First of all, thank you very much, Professor Saleh Naga, for your generous and nice introduction. So today I'm going to speak about one of very interesting topic, which is RNA interference therapeutic in organ transplantation. First, I would like to thank and appreciate the organization of this meeting, and I think this meeting is more, inshallah, will be more successful than the last year meeting. This was from the last meeting, and this is a progressing chapter, and this is, I am very proud by that. Also, I am very proud to be a member with this unique team at Mansoura Urology Referral Center, with Professor Unaim, the founder of the center, and Professor Sobh, the father of nephrology in Mansoura, and all professors and colleagues in this fascinating photo. This team has the experience of 3,115 live donor kidney transplantation. We don't have eculizumab and we don't have RNA interference therapeutic yet, but let me to start the journey of RNA interference therapeutic by this slide. We have DNA in the nucleus, and for DNA to be translated into proteins, we have two pathways: transcription of DNA into RNA, and RNA in the beginning it is premature RNA to be matured into mature RNA before it leaves in the nucleus to the cytoplasm to face ribosome, and ribosome is the machinery for formation of protein. And I'm going to show you in 2.5 minutes video about how the DNA is translated into proteins, because it will pave the way for my presentation. So this is the cell.
In most human cells, there is a structure called the nucleus. The nucleus contains the genome.
So if you go inside the nucleus,
The genome is split between 20.
we'll find the chromosome where the DNA is condensed. Yes, I think this is more better than my English.
Within the DNA are sections called genes. These genes contain instructions for making proteins. When the gene is switched on, an enzyme called RNA polymerase attaches to the cells of the genes. It moves along the DNA, making a targeted messenger RNA after three bases in the nucleus. The DNA code determines the order in which the three bases attaches to the messenger RNA. This process is called transcription. Before the messenger RNA can be used as a template for the production of proteins, it needs to be processed. This involves removing and cutting sections of RNA. The messenger RNA then will be cut in the nucleus into the cytoplasm. Protein factories in the cytoplasm ribosome bind to the messenger RNA. The ribosome reads the code of the messenger RNA to produce a chain to make up the amino acids. There are 20 different types of amino acids. Transfer RNA molecules carry the amino acids to the ribosome. The messenger RNA is read 3 bases at a time. At each triplet is read, a transfer RNA delivers the corresponding amino acid. This is added to a growing chain of amino acids. Once the last amino acid has been added, the chain folds into a complex repeating chain to form the protein.
So this is the most important point, to have normal translation. So if we have normal translation, we have normal protein and we have healthy environment. If this process is disturbed, we will have diseases. And I'm going just to show some events in the history of evolution of RNA interference therapeutics. So RNA interference therapeutic started from the early 70s in experimental work until 2006, when these two guys had Nobel Award for detection of double-strand RNA. And this slide shows the clinical trials within the last two decades about RNA therapeutics, interference therapeutics. Let us to consolidate the meaning. What is the principle? What is the value of the presence of double-stranded RNA? This is the long-strand double-stranded RNA, which faces dicer. Dicer is an enzyme that changes this long double-stranded RNA into a smaller one. And then a smaller double-stranded RNA, there are two phases. We have here the passenger phase and the guiding one. So after meeting this complex, which is RNA-induced silencing complex, the passenger fragment disappeared and cleaved by this structure with the presence of argonautes. At the end of the day, the guiding filament bind to its complementary and stop protein synthesis. So if we want to stop the protein synthesis by this transcript, we should use this element. It is not restricted to double-stranded RNA, but we may use single-stranded oligonucleotide or other complicated phases. So it is not only restricted to the double-stranded RNA to interfere with RNA synthesis. A lot of systems that are currently used in research. And by the way, it is not interfering RNA therapeutic means to stop the bad protein synthesis, but as well includes activation of some depressed proteins. So we have here inhibition of microRNA within the cell, also activation of some RNA. So interfering with RNA may be inhibitory and may be activating or stimulating. The most important step is to have proper carriers, because nucleic acid, if it is injected into the cell, it will be dissolved and fragmented. So carriers are essential. These are the common three carriers, either lipid bilayer or N-style galactosamine, or this simple but yet robust siRNA delivery. A lot of others, lipids, polymers, and as you see, multiple polymers are there. So all the time there is refinement and innovation in the carriers of RNA. And this is the list of publications depending upon the type of the carriers during the last decade. Again, no one size fits all. So there are strengths and weaknesses for each type of carriers. And by the way, the best carrier is viral vector. If we wanted to establish a technique, viral vector transfection is the most potent, but we are afraid of viral vector because it may lead to oncogenicity. This is why the scientists shifted from viral vector into these types of synthetic carriers. Is there any potential applications for this technology? Yes. Since a long time it was used in treating HIV-related syndromes, and for cancer, a lot of research in phase 1 and phase 2, and this is a textbook about RNA interference and the cancer therapy, including more than 415 pages. And for hypertension, we may have treatment. Nowadays, there is phase 1 and phase 2 using RNA interference, either by double-stranded RNA technology or oligonucleotide, antisense oligonucleotides. Both of them can be used to silence, to edit the translation, and to stop angiotensinogen in the liver. So by injecting this double-stranded RNA or oligonucleotide, antisensing, angiotensinogen is inhibited. When angiotensinogen is inhibited, this will add to the treatment armamentarium of RAS blockade. And the advantage is we give this injection less frequent than the usual use of ACE and ARBs. If there is any approved treatment in the medicine, you will be surprised. After the Nobel Prize in 2006, Big Pharma entered the research of RNA to find therapeutics for many diseases. But because of failure, because at the time there was no refinement of the technology, the Big Pharma left the field. Until 2019, when FDA approved the first RNA interference therapeutic based on Apollo trial, which was multi-center, double-blind, placebo-controlled study, phase 3, assessed patisiran, which was used for treating hereditary transthyretin amyloidosis. So by using this drug, the polymers of amyloidosis is inhibited, and this improved so much the neuropathy. And post-hoc analysis in JAMA cardiology next year proved that this drug helped cardiology as well. So nowadays there is a silencer for the transthyretin amyloidosis, and there are two drugs approved in Europe and United States. And it seems that these drugs enriched the treatment of heart failure, as you see here, and transthyretin amyloidosis after a period of stagnancy. And these are the two drugs, the inotersen and the patisiran. The first drug is associated, it is given subcutaneous, so it doesn't need pre-medication, but the problem is it causes thrombocytopenia, and to be cautiously used if thrombocytes platelet count is less than normal, and is associated with kidney and hepatic dysfunction. The second drug, which is FDA approved, is given intravenous, and it is associated with infusion-related side effects, but without thrombocytopenia, renal or hepatic side effect. And this is the cartoon of the two drugs, and how this is the first one, and this is the approved, this drug Onpatro, which is approved in August 2018 by FDA. And this is the technology. This drug Onpatro is transfected through lipid bilayer. So lipid bilayer is the carrier that carries this drug inside the cell, and then the double-stranded RNA is released to inhibit transthyretin and to block amyloidosis. And this is from the starting point until inhibition of amyloidosis. The second drug came after this trial for intermittent porphyria. In intermittent porphyria, there is a defect in heme biosynthesis that lead to skin and neuropathic pain and severe abdominal pain. And the drug is jovuziran, inhibit hepatic aminolevulinic acid synthase, which is a rate-limiting step in heme biosynthesis. And the study was done among these countries, including 94 patients. The drug was finally approved in November last year to treat intermittent porphyria, and this is the drug. And this is how the drug is transferred. Regarding transplantation, is there any studies to use RNA interference therapeutics in renal transplantation or organ transplantation? It seems that RNA interference therapeutics is one of the of regenerative medicine fields. And this is a very nice review that was released last November in the American Journal of Transplantation, discussing these points. In 2018 and 2019, we have here the RNA interference therapeutics used for for ischemia refusion injury model to protect against delayed graft functions. A lot of preclinical studies were carried out in liver transplantation to reduce inflammation, apoptosis, and to target inflammatory pathways to protect the graft from inflammation and damage. I think it is essential, but it's still experimental. Again, for kidney, a lot of preclinical research for lung and heart transplantation. And this another experimental work showed that by interference therapeutic of RNA synthesis, we can keep endothelial cell and the artery by inhibiting macrophage-dependent innate immunity by interference with RNA, and to enhance tolerance again and again. All these studies are preclinical and not human. And last year, this is the first report of CERNA using RNA interference therapeutics for ex vivo hypothermic and normothermic liver machine perfusion. And here, after cannulating the hepatic vein and injecting this CERNA, by this way we can stop fast ligand pathway and to reduce apoptosis, and this may improve the liver transplant and to reduce delayed graft function. Regarding the kidney, one of very important point is delayed graft function, and this is CERNA to inhibit the pathway of P53, and this study, the drug has phase 1, 2, and 3 studies. So this is the clinical study, phase 3, using RNA interference therapeutics for treating an inhibition of delayed graft function in transplantation. This is a very nice review discussing the issues of acute kidney injury after kidney transplantation. And within the discussion of this article, the authors mentioned, based on personal communication, phase 3 study of this drug to tackle delayed graft function in the kidney was disappointing for treating 634 kidney transplant recipients. Another hope is to have drug for primary hyperoxaluria for treating and inhibiting enzymes. And this lumisiran is one of RNA interference therapeutics that stop here this enzyme, which is associated with increasing oxalate. And this is from Renal Week, the abstract of the the preliminary study of phase 1 and phase 2 for using this drug to reduce oxalosis, and the results were beneficial and were promising. As you see, even the preliminary data of the phase 3 study of this drug may carry a hope for patients with primary hyperoxaluria to reduce oxalate deposition, and because this is a real challenge. The most important point is how to face the challenges of RNA interference therapeutics after refinement of the carriers, to know the pathways, because RNA may be degraded by endonucleases or even phagocytosed by phagocytes, or there may be a barrier to enter the cell membranes because of barrier negativity, or even inside the cell, the RNA may have exposed to exocytosis or other mechanisms. We are waiting the more and more refinement of carriers, so this is nanoscale, and I think the most important challenge, as Professor Foda mentioned, that eculizumab is very expensive. Here, these are 3 drugs. This drug is used, this RNA interference therapeutics, in muscular atrophy. So it is approved, but the cost of treatment is heroic. $750,000 for the first year, then $500,000 every year. So very expensive. And the other 2 drugs for amyloidosis, $500,000 every year. So a lot of challenges are there. We need to improve how to escape from endosomes, from toxicity, to have other alternatives. And I think these are 2 very recent articles that will appear in this issue in coming June, showing that we may improve the RNA protein based on nano device. So we may have dedicated nano device, or even aptamers, which is the switch on and the switch off of the translation. And the purification of RNA therapeutic may be another challenge. And using even natural and rapid, using the spherical nucleic acid technique. So to reach my conclusion, one day we would be able to achieve a knockout of all diseases caused by genetic defects. Maybe this may be a very dream hope for Borgeria, Alzheimer, tumors, oxalosis, ischemia, refugial injury. However, the use of RNA interference therapeutics in the field of kidney transplantation is still in its infancy. But I think the data of primary hyperoxaluria is promising, and to reduce primary hyperoxaluria and to have drugs that stop oxalate deposition, I think this will be a great success for the patients. And I'm also, you'll find this whole presentation of this chapter will be uploaded to the Egyptian Society of Nephrology Virtual Academy, inshallah, after this meeting. And at the end, I would like to thank and appreciate the efforts done by my great brother, Professor Ayman Rifai, for the establishing a very prestigious program. Thank you very much for your listening.